Welcome back, idea mechanics. Today, we're looking at the structural logic that drives modern hardware, moving beyond the random eureka moment to the systematic discipline behind industrial breakthroughs. Take this slow-motion footage of a plastic button snapping under pressure. No matter how much effort goes into the design of a traditional mechanical switch, the simple reality of physics dictates the outcome. This cross-section shows the vulnerability. Every time physical contact closes a circuit, you introduce friction and microscopic material fatigue. Yet the industry spends millions engineering slightly thicker plastics, only to watch them fail at the exact same friction points. Before we dismantle that cycle, subscribe to the channel and hit the notification bell. Then join the conversation below. What hurdle should we tackle next? To solve this, engineers have to move past the idea of building a better button. We need to look at the nature of physical mechanics through a different lens. The navigator is reviewing a high-tech blueprint for Principle 28, mechanics substitution. It contrasts the physical limitations of a coiled spring with the precision of a light beam, posing a simple question: what if we removed human force from the equation entirely? By substituting physical wear with invisible forces like light or electricity, a device moves from a fragile reactive state to a design built for frictionless operation. In sensor design, the primary contradiction is detection versus degradation. A device needs to recognize user input millions of times, but a physical switch creates a point of failure that worsens with every single use. The schematic shows the fix. Left, the standard mechanical circuit. Right, an optical sensor setup. It uses an unbroken beam of light. An object passing through triggers the circuit instantly. Unlike the mechanical side's physical strike, this setup performs the same task with zero contact. This substitution yields immediate gains in precision and response time, while nearly eliminating the need for maintenance or repairs. For the user, this removes the physical limits of the hardware. It changes the standard for how long we expect our devices to last. There is also a conflict between mechanical bulk and sleek design. Consumers want seamless surfaces, but physical buttons require gaps and moving parts that inevitably stick or break. The second solution is electronic substitution. A sensing grid sits beneath a solid, seamless surface, projecting a digital electrical field. As a finger approaches, the field bridges to the skin. This disruption triggers the circuit below instantly, without the outer surface ever needing to bend. This creates an uninterrupted interface. The hardware becomes a smooth, solid object because the controls have transitioned into an invisible electronic field. Real design innovation isn't about the color or texture of a button. It's about replacing the mechanics of touch to enable device shapes that used to be physically impossible. We've seen the before state, clunky springs and plastics destined to fail, and we've seen the after, the resilient performance achieved through optical and capacitive sensors. Engineers behind high-end consumer electronics don't just build stronger buttons. They look for ways to remove mechanical friction from the system entirely. This makes innovation a repeatable architectural skill. Frameworks like Principle 28 turn futuristic concepts into practical, reliable hardware. My thanks to the Navigator for the blueprint breakdown, and to all of you in the Idea Mechanics community for joining us. By mastering systematic discovery, you no longer accept the fatigue of traditional mechanics. The tools to design systems that outlast their predecessors are already in your hands.